It's my pleasure to welcome you to PARC. My name is Scott Elrod. I manage one of the labs here at PARC, the Hardware Systems Lab. So I'm happy to introduce our speaker for today, Dr. Ilan Gur. Ilan is a program director at the Advanced Research Projects Agency for Energy, ARPA-E. His technical focus includes the electrical and thermal sides of storage, battery management, solar energy, as well as new materials for energy conversion and storage. He's also an advisor, senior advisor to the technology to market activity within ARPA-E. He spent his career developing a number of clean technologies with startups and also in graduate school. He was co-founder and director of CO, which is a venture-backed lithium battery startup. And he helped bring the the lab stage chemistry into, into realization. Previously, during his PhD research at Berkeley, he developed a new class of low-cost photovoltaics, and that work served as the basis for Selexant, a company which is working to commercialize the technology. Ilan has a PhD, master's, and bachelor's from UC Berkeley, all in materials science and engineering. He also serves on the professional faculty at the Haas School in Berkeley. So it's a real pleasure to have you here. I'd also say it's a pleasure that Ilan is the program manager for one project that we have funded here at PARC by ARPA-E. So welcome.
Right. Thanks, Scott. Now you know why I was invited, because I actually run a program here. No, I'm just kidding. Thank you guys for sitting through the winded introduction. I'm really excited to be here to share a little bit about an agency that I work for, really proud to work for, called ARPA-E. Some of you may know about it, others may not, and I'll introduce it. And I'm going to talk a little bit about our model for encouraging innovation in the energy space at ARPA-E, and we'll use as a bit of a case study some of the activities and work we're supporting to develop a next generation of electric vehicles, and specifically the battery technology to drive it. So I'm excited to give you a glimpse into the future of EV batteries. Before we go into the future, I wanted to take a quick glimpse into the past. So let's see if this works.
1957. We are ensnared in an arms race with the Soviet Union. Then, in October, the Soviets launched Sputnik, an implicit threat that shocked the nation.
Today, a new moon is in the sky, a 23-inch metal sphere placed in orbit by a Russian rocket.
Our satellite program has never been conducted as a race with other nations.
Eisenhower instructs his new Secretary of Defense, Neil McElroy, to coordinate our national space program. The Soviets had surprised us.
We thought of them as being dangerous, and to have them show up ahead of us in this new, seemingly terribly important technology was a shock.
ARPA was formed in February 1958 as a special agency in the Pentagon, reporting directly to Defense Secretary McElroy. Its charter: maintain U.S. technological superiority over potential adversaries.
And the way he put it was, he said, I want ARPA to do those things which otherwise fall between the stools.
ARPA's initial focus was 3 presidential initiatives: get us into space, protect us from Soviet missile attacks, and detect Soviet nuclear tests.
I don't think I ever realized how scary Sputnik must have been until I saw this picture. You see the damn thing, and it gives you the heebie-jeebies, right? And so I think it really crystallizes the idea that, in 1958, Eisenhower really created the original ARPA agency, now known as DARPA, really kind of out of fear, out of shock that this really scary thing was circling above, and feeling like, wow, the U.S. may be really falling behind in a critical area, aerospace and defense. It was almost exactly 50 years later, in 2007, that Congress created the agency I now work for, ARPA-E. And the agency was created based on the recommendation of the National Academies of Science and Engineering, who said, yes, this was a major threat in the last 50 years. We've sort of overcome that threat. In the next 50 years, one of the biggest things that's going to drive the global economy, geopolitical stability, national security, environmental security of the world and our country is going to be energy and energy technology. And by the way, similarly, there's a pretty big risk that we're falling behind as a country. The report, which you can look up, is called Rising Above the Gathering Storm. The national academies have done a couple of these now, and there is a lot of data there which kind of makes you stop and say, well, this is concerning. Although I never put it, the image, the scary Sputnik image, I thought, this doesn't really apply. What are these Sputnik moments that we're talking about that sort of make us freeze in the energy space? And if it seems melodramatic, I realized there are these moments happening. If you look at the global race to sort of capture the opportunity in energy technologies, and they continue to happen today. So I'll give a few quick examples. Some of you may have read just earlier this month, probably in any major newspaper, the news that Japan has claimed to be the first country in the world to be able to extract natural gas from deep sea methane hydrates. I think the significance of what's been done is still open. We'll have to learn more about what's happened, but this is potentially huge, right? Methane hydrates could provide a larger energy resource than most fossil fuels that we depend on today, making many countries in the world energy independent with the ability to depend on this source. So that's a big one. I'll give you a different example from last year. This is May. On this cloudless day in May, this is just a picture, this wasn't the actual day, right? But on a cloudless day in May, Germany produced 22 gigawatts of electricity from solar energy. That just about meets half of the peak electricity load on the German grid. About 10 years ago, I worked on solar and photovoltaics in particular, and the idea that any country, let alone a advanced industrialized country like Germany with an entrenched infrastructure, could get half of their electricity demand from an intermittent renewable energy source like solar was crazy, right? I think most people thought, that would never happen, or not for a long time. And I think even in the US today, we have arguments over, for parts of the country, can we support 20%, 30% renewable integration and at what cost? This is happening now. They were the first to run this experiment, okay? That same month, May of 2012, there's only one more here. This isn't going to go on for the whole time. Norway opened their Mongstad Technology Center. This is the largest, most advanced research and test center for CO2 capture in the world. And it happened in Norway. And so, I wanted to kind of put these evocative images up. Obviously, what hopefully you're thinking in the background is, these are interesting tidbits, but this isn't quite Sputnik, right? And by the way, Japan and Germany and Norway, they're not really our fierce enemies, right? And so obviously it's not quite the same, but I think it illustrates the point that a lot is happening globally and not necessarily here in the US in a lot of these areas. But I want to point to, these aren't Norway, Japan, Germany, these aren't the villains in the story like the Soviet Union may have been in the Sputnik days, at least perceived. But there are villains in the story. And so if I look at the mission that ARPA-E was created with in the charter from Congress, it's to catalyze and support transformational. So we don't support incremental technologies. We're really looking for big game changers in the energy landscape of technology to ensure America's technology lead, similar to the original ARPA or DARPA, but with really three very specific goals. And these are the villains in the story. The first is to kind of beat our dependence on foreign energy sources. So today, we still send about $1 billion a day overseas to sort of fulfill our energy addiction, oftentimes to countries we may not agree with, whose names we may not be able to pronounce, countries in which a political event, a small political event, could drastically disrupt our well-being in many ways, politically, national security-wise, et cetera. So that's one. The second is to deal with our energy waste. So in the US, we waste more energy than we use. And I try and get my head around it. The best analogy I could come up with is, if I go out and I buy the ingredients for this wonderful meal and I spend a bunch of time making it, and then as soon as I bring it to the table, I have to throw 60% of the meal onto the floor, that would make me pretty upset. And that's basically what we're doing on a minute-to-minute, hour-to-hour, day-by-day basis here in the US. And then, of course, I think the biggest one, and maybe the one that has the biggest analogy with Sputnik, is emissions related to energy use. Okay, and so when Sputnik was flying overhead, I think it was this harbinger of doom, but it was an implicit threat. I don't think initially anyone really knew, well, what are the real implications of this, to our future security? I think the analogy here is when things like Sandy happen, right? There's a harbinger, there's an implicit threat. We may not know exactly what that means for the future, but there's a risk there, and there's a need for response. And so I think that really sort of gives some insight into why this is a bit of a Sputnik moment and why ARPA-E was created. In the end, ARPA-E is a funding agency. We're an R&D funding agency for the government. We sit within the Department of Energy. Like ARPA that reported directly to the Secretary of Defense, we report directly to the Secretary of Energy. And I'll just mention here, and we'll spend a lot of this talk, I'll give some insights into how we catalyze and support innovation and transformational technologies. I'll just mention here that it doesn't say that our mission is to fund technologies. That's what we do, but we see that as only one part of what we do, right? Hopefully, if we're successful, our role in making these transformations happening is not just the money, but is in inspiring researchers across the country and trying to create a vision for where we could be going technology-wise in energy, and really building communities to support these ecosystems. So we'll talk more about how we do this, how we catalyze these things, but I want to quickly start by saying what we're trying to catalyze. So this is a little bit about our approach, and because we're going to be talking about the automotive space, I'll use an automotive example here. Generally, with ARPA-E, we think about trying to create new learning curves for technology. And the learning curve is a very simple concept. If we take a conventional technology, let's go back to the horse and buggy carriage days. If we look at that as the state-of-the-art technology at the time, over time that technology will get better. Right? And by better, I mean the performance will get better, the cost will go down. Okay? And it'll happen incrementally. And at any given moment, based on other things happening, other technology developments, other things happening in the world, there is an opportunity that new ideas might be there that could potentially be transformational, that could potentially change the way things are done. In this case, right, the Industrial Revolution happens, and you have a bunch of crazy folks out there saying, you know what, we're not going to depend on horses for personal transportation for much longer. We're going to have these big bulky machines that run in these things called engines, and they're going to be powered by fuels. And I think the important thing to keep in mind is if you could freeze frame, right? Back then it wasn't called the Industrial Revolution, right? It was just happening, right? So if you could freeze frame back then and you thought about these folks who were talking about what the future might look like technology-wise, you'd say, well, these guys seem kind of crazy. They're telling me that these new technologies are going to be better, but if I look at their steam-powered, carriage, what I find is that it's way more expensive than my horse. And by the way, it's way louder and it's super dirty, and I don't really know exactly how to feed the thing. And if I'm on a long trip, my horse will eat some grass. What am I going to do here? Right? So they generally start out not looking as attractive as what the state of the art is. But as we know, they have the potential, right? If the Industrial Revolution does end up happening, these things will ultimately win. Which one of these concepts will win? And this is one of our big philosophies at ARPA-E. If you went back in time and you said, well, which one of these concepts will ultimately change the way things are done, you probably wouldn't be able to pick, right? And ultimately, and I'm, here this is the Model T as the example, ultimately only one or maybe only a few will. And so this is kind of the first lesson that I'm going to throw out from what we've started to learn in ARPA-E and our philosophy, is just take lots of shots on goal. Right? When you're trying to think about the future state, And even if you kind of know where it might lead, it's hard to know exactly what's going to win out, and so you need lots of shots. So let me give you an example of sort of the power of lots of shots on goal and how we do things at ARPA-E. And generally speaking, I'll be talking today about one of the big goals that we've had at ARPA-E. We have a lot of different things we're working on, but if you think of our mission area, reducing emissions, reducing our reliance on foreign energy, increasing efficiency, moving our transportation sector to one that relies on electricity instead of gasoline, imported gasoline, will have a huge impact on all three of those potentially. And the sort of challenge that we've set up to be emblematic of that is, could you imagine an electric vehicle, just like surpassing the horse and carriage buggy, hearse and buggy carriage? Could you imagine an electric vehicle which could basically give you similar performance to the vehicles we're all used to driving today, and do it cost competitively? And so the challenge in our mind is, could we have a vehicle which could put you on a trip from Chicago to St. Louis with one charge, kind of one fill up at the gas station, and can you do it competitively? So the good news is, if you had this imaginary electric vehicle, this trip from Chicago and St. Louis, that tank of gas would only cost you about $7. And tank of electricity, right, would only cost you about $7. So that's pretty good. That's attractive. And the thing would be pretty quiet, and it would handle nice, and it might have good acceleration and torque because it's electric. Obviously, you probably understand the downside here, which is, based on today's battery technologies, to have this car, you're talking about a battery alone that will probably cost upwards of about $30,000 and weigh almost a ton. Okay, so we're not there. It's a nice idea, but we're not there. And so one of the things that we've been supporting is, how can we drive innovation in the energy storage space for transportation? So a little bit of history before we jump into that. So these two pictures show the first two batteries ever commercialized. First two real batteries ever commercialized. So Plant in 1859 came up with a very elegant electrochemical couple based on lead oxide. Leclanche in 1867, right around the same time, said, I've got a really interesting battery chemistry based on zinc and manganese oxide. And if your brain's not already there and you don't recognize these, they may look more familiar in this form. Okay, so it's actually kind of funny. I laugh because I say, at least with the alkaline battery, they came up with some snazzy new packaging, right? The lead-acid battery looks almost exactly the same. And actually, in terms of the fundamentals of how these things operate, they're not that much different. And here's the really fascinating, scary, humbling part, is that if you look at the global market for batteries today, these two battery chemistries are still more than half of the global market. Okay, the first two battery chemistries ever developed. I'm noticing that my next slide doesn't have a title. So this is slide A. And in Exhibit A, I'll show you, this is what we're plotting here is energy density as a function of time. So this is sort of the history of battery development. And now I'm just going to plot the rechargeable battery, the major rechargeable battery chemistries that have been widely adopted. So you guys are familiar with lead acid. We just showed the picture 1867 or whatever it was. And then we went to nickel cadmium, and then we went to nickel metal hydride. And if I stop here, I used to like to joke, this is the Moore's law for batteries historically, with no offense to Moore, right? It actually would look kind of like Moore's law if the y-axis was log scale, but it's not, it's linear scale. And so rather than doubling in performance every 18 months, we have a doubling in performance every 70 years or so. And so this is just really hard. And it's really hard because we're dealing with very complex chemistries. I have a friend who teaches material science at MIT, and he says, I love batteries because basically I can teach all of material science and probably all of chemistry and probably all of physics by just looking at the operation of one battery. And he's right. And by the way, all of the details of operation in every battery looks different for each chemistry, right? So up until modern technology and material science came about, this was a really hard problem. It's still a really hard problem. What few people realize, I think battery development gets a bad rap, what few people realize is that the lithium-ion battery actually has already disrupted this curve. Okay, so 15 years ago, 20 years ago, no one in this room probably knew what a lithium-ion battery was. You certainly weren't using them maybe yet, maybe 20 years ago if you were right on the edge. Today I've got 1, 2, 3, on my person at every given time. Probably a couple more in my bag over there, right? In 20 years, we made about as much progress in lithium-ion development as we did for 50 to 70 years before that. And so we did find that with modern science, we were able to find a platform for battery development which was much more robust and much more flexible for development than anything that had happened before. And we showed that we can make more progress. And the question is, to what limit? And so when we came at ARPA-E in about 2009 and we said, okay, we've gotten good progress with lithium-ion, we need to do way better to meet the target that I talked about and have that vision become a reality, we said, how much farther can we push things? And we basically started with this plot and we said, okay, this is energy density now on the x-axis. Here's lithium-ion today. We're at 210. This is circa 2008, 2009. We're at 210 watt-hours per kilogram. We started a program called BEAST where we said, we'd like to get to twice that. We'd like to double the performance, not in the 57 to 70 years historically, because we know we can do better than that, and actually not in the 20 years that lithium-ion has done it. We want to see, can we do it in 5 years? With kind of the no more shots on goal approach, right? A lot of the research community and a lot of the funding from the government, because lithium-ion was doing so well, was focused on lithium-ion. And so we said, it doesn't have to be lithium-ion, right? You've come up with whatever crazy new ideas you have. Can you get us to 400 watt-hours per kilogram quickly? And we put out a solicitation. We got proposals from across the country. We got hundreds of proposals. We could only pick a handful. And we decided we would fund not one idea, right, but a whole portfolio of ideas all competing to meet this goal. And so here are some of them. So these are some of the other chemistries that we're funding under this program. We're funding, I think we chose, I think, about somewhere around 14 projects that we funded under this effort. They're not all on here, and I'll get in a second to why. But here are some of the ones that we funded. And you'll see it's a variety of new chemistries with potentially far even exceeding the goal that we had. Now, not all these chemistries were new. A lot of these had been tried in the 1800s, and the idea was, well, with modern science and technology and new developments elsewhere, we think we have a new approach to the idea that might actually make it work today. Others kind of were pretty new to us, and we even got 1 or 2 proposals that we ended up funding where we said, they're not on this chart because we actually couldn't characterize them as a battery, right? They were actually sort of new ways to store electricity. They reasonably could get to 400 watt-hours per kilogram, and they just came out of the blue, not things that we were expected. And so the second thing I'll put up here is, for us, it's very important for us to try and constrain, whenever possible, when we go to the community and say, help us solve something, we try and constrain the problem, not the solution, right? Because if you constrain the solution, you might limit what you get back, and you don't have the opportunity to be surprised by the ingenuity of the research community. And so I think the BEAST program is a good example of that. So with BEAST, we're pushing the limits of energy density in batteries. We actually have a project that's already shown the 400 watt-hours per kilogram. It's not commercial yet, and so this thing has only been around, the agency's only been around for 4 years, but we're hoping we're going to get there pretty soon. And it is accelerating pretty quickly. And so the BEAST program was exciting for us because I think it was our chance to sort of chase the dream, what I would call the traditional dream of battery development, which is, what is the next big chemistry, right? What comes after lithium-ion? That's the dream. When we assessed, after doing BEAST, our portfolio of what we were funding, it occurred to us, well, let's not get so busy chasing this dream. It's an important one, but let's not get so busy thinking about what the next big chemistry is that we lose sight of the fact that with today's commercial lithium-ion batteries, we don't do that great of a job utilizing them. We don't do that great of a job getting out the full potential of the chemistries that we have. And so let me give you an example of what I mean by that. So this is a program called AMPED, which I run at the agency. All of our programs have these funny acronyms that normally in real time I can't remember what they stand for. Because I run this program, I know this one. AMPED stands for Advanced Management and Protection of Energy Devices. And so the whole question about AMPED was, we actually don't get as much as we could out of the systems that we have today. So while we're thinking about new systems, let's focus on how do we get way more out of the systems we have today. And I'll give you sort of an example. This is a simple block diagram, basically thinking about how do we design a battery system for something like an electric vehicle. Okay, so the first question you have to answer is, how big does the battery have to be? And that should be a pretty straightforward question to answer. You know, I know what vehicle I'm trying to move. I know the weight of the vehicle. I know the rolling resistance because of the tires. I know the aerodynamics of the vehicle. And so I can pretty easily calculate how much energy does it take to move that hunk of mass 1 mile. And you know, so for an average sedan, that might be something like 200 watt hours for every mile I want to move the vehicle. And I multiply that by the number of miles that I want the range of the vehicle, right? So I'm designing a car with a 100-mile range, whatever it is. Multiply those things out, and I get amount of energy storage that I need to deliver to the car to move the car, okay? So you say, okay, let's go buy those battery cells. Okay, end of story. It turns out it's not the end of story. When we actually design these systems, we get those battery cells, and then we go and we add a bunch more battery capacity to the system. So we make the system bigger. And we add what I'm calling here overhead capacity. And basically the idea here is that we know if we operate one of these batteries right to the extremes of their operational window, at those extremes, that's when a lot of the issues that a lot of the degradation mechanisms, a lot of the reactions in the battery that lead to low lifetime, potentially lead to safety incidents happen at those extremes. So if we double the size of the battery, now I can still get my 100-mile range or whatever it is, but I only operate within a very narrow window of the battery, and that's much safer. I feel a lot better about it. And so we've added this overhead capacity, and then we're not quite done yet because we still need a system. These are just cells. We need a system to build around the cells. So the balance of system includes the physical protection of the battery, it includes the thermal management of the battery, the charge balancing, et cetera. And all of this is needed to basically make sure that we have a reliable, robust, safe battery system. Now, one of the things that we try and think about at ARPA-E when we think of a program is how much headroom is there for improvement? And the way we ask that is, how far are we from the theoretical best that we can do? And so if I look at this problem, I say, well, the theoretical best I could do is drive the car with just the cells that I need to move the car, right? I probably won't, that's kind of super theoretical. I probably will never be able to get there. But in today's commercial systems, on a weight, volume, and cost basis, we're way bigger than that at the system level. We're 2, 3, 4, 5 times bigger, depending on whether you're talking about an EV, a plug-in hybrid, or a full hybrid. And here's the rub. Even though we've put all this extra weight, volume, and cost into over-designing the system, conservatively designing the system, it's not like all the problems have gone away, right? So we still worry about lifetime in commercial systems. Safety, even in some of the most conservatively designed systems out there, is still a liability, okay? And at the same time, we limit the way we operate these batteries. So we're still limiting their charge rates because we're worried about some of the reactions that could lead to safety issues. We talk a lot about dual use. So I buy an electric vehicle. I know it's going to be expensive. One thing that I'd like to do is recoup some of my investment by plugging my vehicle into the wall and letting the grid use my battery unit while I'm not driving. It's a nice idea. And I know I'll get a little change on the side by doing that from the utility, or at least in theory I could because I'm providing a value. What I don't know is how are those extra cycles going to actually influence the long-term reliability of my battery. And so I understand that there's some benefit. I don't really know what the cost is, and so I'm not willing to do it. And so all of this is to say that, we've got all of this extra design, we still have issues. And so the question is, how do we do better? And can we do better? And to answer that question, the biggest question, second question you need to ask is, well, why do you have all this extra stuff on your battery? What exactly is it that we're so scared of that we're trying to protect against? So let's talk about what we're scared of. It turns out that the two things we're really scared of is, one, that the battery is going to degrade quicker than we would have hoped. And everyone who's owned a laptop is intimately familiar with that issue, right? Which is after a couple of years, all of a sudden you get on the plane and, right as you take off, the thing's running out of batteries and you're really frustrated. Obviously in a vehicle, that's not going to work, okay? The other is that these systems, especially the high energy density systems, are very energetic. And we can have significant safety events that we need to worry about. So those are the ultimately things that we're worrying about. What leads to that? Well, what leads to it are basically a bunch of reactions that can happen inside every cell in a battery that are physical, chemical, electrochemical reactions. So I've listed, this isn't a comprehensive list, but I've listed a few of them. So inside any given cell in your battery, you might have a case where at high state of charge or at high power, you actually have a reaction of the electrolyte with one of the electrodes, and that leads to capacity fade, it leads to power loss. One of the big ones we're concerned with from a safety standpoint is something called dendrites. So talk about Sputnik as the scary image, right? Dendrites are a scary idea, right? Which is you go to charge your battery, and normally what happens is the lithium ions find their way into your graphite anode of the battery, and they kind of sit inside, and you're happy and you're charged, right? If it so happens that you try and charge too quickly, or maybe you try and charge at too low of a temperature, or maybe you try and charge at too high of a state of charge, rather than going into that anode, into the electrode of the battery, the lithium might just decide to pile up on the surface. And so what happens is you now form a bunch of pure lithium metal on the surface of your electrode. It forms a filament, right? Now it's getting scary, right? And the filament makes its way across the battery cell and shorts the cell. And by the way, the lithium is extremely reactive, the electrolyte's extremely reactive, and the whole battery can potentially blow up. Okay, one of the things we're really scared about. The thing to keep in mind is that's something that's happening inside any given cell in your pack, and it's physical. It's happening in there. And so you say, these are the things that we're scared of. Now, what occurred to us when we thought about the way we do battery management today is that these are the things that we're scared of, but when you look at what we actually monitor to design our systems and to control our battery systems, we don't monitor any of the stuff that we care about and that we're scared of directly. We monitor things that are pretty easy to monitor, right? So we monitor temperature, we monitor voltage, we monitor current, and they're pretty basic measurements that we're doing. So when we started thinking about this space and thinking, can we do better in battery management, we went out to the community, and one of the first things that got our attention from a technology standpoint was that there seems to be an implicit assumption that these are the only things you can measure, and these are the only things you can monitor. And the implication of that is that when we're designing systems and when we're controlling systems, this is basically the situation, right? We're sort of flying blind, right? Because we don't know what's happening in any of the cells, right? Rather than right-sizing the system, we have to oversize the system, right, to the most conservative case. And rather than controlling the system optimally, we have to control the system really conservatively, okay? So we basically asked the question, what if we could remove the blinders, okay? So for us, this is kind of one of these, again, one of these sort of lessons that we've learned, which is there are these implicit assumptions that experts in a space just, absorb over time, and questioning those assumptions is really important to us. So for instance, when we think about a new program, we generally hold workshops with industry, with outsiders out of the government, to talk to them about their ideas about a space. And we try and question assumptions, and often we try and question by bringing in people from other spaces, right, who aren't ingrained in batteries, right? And so one of the catchphrases we have is, if you want to think outside the box, don't invite the box, right? So we don't necessarily only want experts who are going to taint with their assumptions, and we want to try and question those assumptions. So the exciting thing about the AMPed program is, again, without constraining the solutions, we put out the problem there and we said, could we remove the blinders? And we had a lot of ideas. We thought, well, rather than taking temperature measurements on the surface of cells, what if you could get inside of a cell and get internal temperature data in real time? What if you could get strain data? No one looks at strain of these cells, but we know that can be correlated to some of the operational parameters, safety parameters. When we got our proposals back, we ended up, like the Beast case, getting a bunch of stuff that we didn't expect. And one of the things we got were a number of proposals that said, hey, there's a lot of interesting stuff going on with optical detection these days. It's getting cheaper. It's getting more powerful. We don't think anyone's ever applied this to batteries. Now, from ARPA-E standpoint, this is exciting, right? Because we hadn't really thought very much about optical. And what we're finding is not one person in the country, but several leading researchers in the countries are all telling us at the same time, hey, optical is interesting. And so we said, this might be one of those big inflections, right? There might be an industrial revolution, right, going on here that we have to pay attention to. And so we funded a couple of efforts, and this is one of the efforts is here at PARC that we're really excited about. So at the top is the team from PARC working with a leading cell supplier. And PARC basically said, what if you, rather than having the normal sensing and monitoring system you have today, what if you had a fiber optics-based monitoring system for your battery? And if you could do that based on some really innovative, cheap sensor units that PARC has developed separately, if you could do that, we could basically get you in a very cheap way temperature data, but also strain data, maybe even chemical composition data, and we could even think about wiring these optical fibers inside of the cells and get data from inside of the cells, which no one's ever done before. Super exciting, right? At the other side of the country, a team at Battelle totally separately had a brainstorm, and they said, you know, we're really interested in dendrites. Dendrites are really scary. How the heck could you ever detect a dendrite growing inside 2 of your electrode layers? These are 200 microns thick in a battery. And they said, well, what if you scanned it optically inside the cell? And so very different idea, but really coupled. And so these are 2 of the efforts that we're funding under AMPed. This is all about trying to remove those blinders. What we realized in developing the program is that removing the blinders is important, but it's just one step. And what we actually need is a bigger community of interdisciplinary folks thinking about this problem. And I'll give you a little sense of why that is. So if you remove the blinders through better sensors, and this is a list of, again, the portfolio. We're funding a lot of different projects under AMPed. If you have better sensors, you have a better sense of what's happening inside the cell. Okay? We realized that there's another way to get a better sense of what's happening in the cell. Right? Rather than come up with a lot of bells and whistles in terms of fancy new sensors, what if you just took that indirect data and had better modeling to let you know what was happening inside the cells? And even if you did have better sensors that are based on the physics, right, monitoring the physics or electrochemistry, you probably need models that depict the physics and electrochemistry to go hand in hand. So those things go hand in hand. If you know more about what's happening in the cells, you then have to decide what are you going to do with that information. So you need better controls, more adaptive controls, technologies for these batteries. And then you need a system that can actually respond to the decisions you make from a control standpoint. Today, the systems in batteries are very passive, right? So can we think about more active, more dynamic thermal management systems, power management systems, et cetera? So here's the AMP program. We talked about BEAST. BEAST was all about pushing to high energy density. And AMP says, well, right? Whenever you're at high energy density, you're really scared of all this stuff, so you need to build a protection unit. And then if you think about it, if we push to even higher energy density, we'll probably need even better protection. And so these things go hand in hand. As we were doing AMPed, we realized something else, which is we bounced the AMPed concept off of folks, and we got input from the community. And one of the responses we got was, if you're trying to solve the problem of all of this extra capacity in these cells to protect the cells, right? What if we thought of a different way the future could look, right? Rather than assuming that we're always going to develop higher and higher energy density batteries and we're going to need to have better and better protection for them, what if we imagined trying to come up with a battery that doesn't need any protection at all, or doesn't need any controls at all? In which case, you basically get rid of the top of this curve, and you have a battery which can just sort of stand alone in the limit. I can't say much about the AMP program because it's out there now, but that's kind of one of the ideas behind AMPed. And I think it invokes the lesson which we have at ARPA-E, which is, with each of these programs, we're trying to come up with a vision of what the future could look like, right? But the lesson is, don't try and predict the future. Try and predict every possible future, right? So with range, we have a program that's basically antithetical, right? We've got 2 programs that are just completely different and don't make sense together, but that's good for us, right? Because we're not sure which one of them is going to happen. And so at ARPA-E, when you look at the full spectrum of what we're funding, that's exactly what we're doing. We're trying to predict every possible program. So here are all those acronyms. I told you all of our programs have these acronyms. You can go to the website and learn what each of these programs is, but basically from transportation technologies to stationary technologies, we're funding different programs, and it's not that they all fit one version of what the future could look like, because we can't predict. They fit different versions. And so while we're trying to develop better electric vehicles, we also have a program called MOVE, which says, well, we just found a ton of natural gas in the US. Why don't we try and come up with storage technologies for natural gas so that we could have a very cheap natural gas vehicle that you could use as a consumer every day, right? Maybe one of those things happens, maybe both of those things happens, all right? But our view is that our job is to create the option technologically for these things to happen and go from there. Separately, we have a couple of alternative fuels projects, which basically says, no, 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 don't change the car. Leave the car the way it is. Change the fuel to a fuel we're more comfortable with. And again, we have not one but 2 different programs in that way. So I'm getting towards the end here. I wanted to just put one more lesson. Because I'm here at PARC, I know a little bit about the history of PARC, and I tend to think about it as, PARC was a place that was developed by a bunch of genius hippies sitting on beanbags, right? Is that Is that fair? Is that part of the legacy of this place? So I'm guessing that there was some meditation that went on here. And in meditation, there is this concept of a beginner's mind, right? This concept of try and bring a fresh set of eyes and a fresh mind to everything that you do and every interaction you have in the world. And so this is something, and that was kind of meant to be a joke, but this is something that we found is actually very, very powerful. It goes kind of hand in hand with this idea of questioning assumptions. But I'll tell you the story about the last program that we have that falls into energy storage for cars. And this is a program that started in the agency by a colleague of mine, Ravi Prasher, who's one of our program directors. Now, Ravi is an interesting program director. He came into the agency having very little background in the energy space. He wasn't, fired up about solving the energy crisis, for 20 years. He was running, before ARPA-E, he was running a research lab at Intel, working on new ideas for better thermal management of computer chips. And he came into ARPA-E, and for the first time, he started thinking about energy and thermal management, not at this scale, but at the global scale. And so the first program that he ran is a program we have on dramatically increasing the efficiency of air conditioning systems, right? So that made sense. And then he was thinking about, what else can I do? And he started walking around saying, it's interesting. Everywhere I look, I see something about batteries. Batteries this, batteries that, energy storage this, energy storage that. It's hyped so much. Every issue of Science, every issue of the New York Times, I see something about batteries. And he said, why is it that we're always talking about electrical storage? Right? He said, I'm a thermal guy. Basically all of the energy that we use in the world at some point in its life cycle ends up as heat. Right? So electricity is just a small portion of what we use. Why aren't we thinking about batteries for heat? And it was a good question, right? And one of the things that we talk a lot about at ARPA-E is white space. And so we saw this as a white space, not because no one has ever thought of doing energy storage for thermal systems, thermal energy storage, but because we basically went out there and looked at what people were doing. And what we found was there were a number of researchers working on really interesting problems related to thermal energy storage. But there wasn't a really strong community like there is in the battery space, right? And most of these researchers were working on the fundamental chemistry, but they weren't really fired up about any problems they were solving. I shouldn't say that, right? I'm not meaning to disparage the community. There weren't that many really exciting problems in energy that they were banded together around to solve. And so this goes to the point of not just bringing funding to the table, we're trying to bring something more. And so we said, well, maybe a role we could play here is to fund and build a better community in thermal storage, but also highlight some of the big challenges and big opportunities for thermal storage. And as we went and explored that, one of the things that we found that was pretty interesting related to electric vehicles. And so here's the scenario. You went out and you bought your 100-mile electric car. Because you've got a 40-mile, your work is 40 miles from your home. So every day you have an 80-mile commute. And so you say, great, a 100-mile electric car. I just have to charge my car at home. I don't have to worry about it when I'm on the road. And then it just so happens that winter comes. And in the middle of the winter, you decide to drive to work. And you turn on your heater and you're driving. And on your way back, your car runs out of batteries. Why? Because rather than using the entire battery for driving the car, you've now used a chunk of the battery to heat your cabin, okay? And so it turns out lithium-ion batteries make very expensive heaters, right? Cabin heating and cooling, and I sort of blocked the number, but it might not be that surprising, it may be, right? But in an electric vehicle, the effect of heating, if you drive with the heat on all the way to max for the whole trip, which you might do in Minnesota or elsewhere, can reduce your range by 35 up to 40%. Okay, so now your 100-mile electric range is 60 miles electric range, and you can't get to work. And that's a big problem, okay? Not to mention this fact that for the scientists sitting in the room, you should be cringing, right? What are we doing here? We're taking fossil fuels, we're combusting them to get heat, okay? We're then converting the heat to electricity at a major loss. We're spending a lot of money to move that electricity through the grid. And then you're taking that electricity, you're charging up a really valuable, expensive lithium-ion battery just so when you're on the road, you can resistively convert back to heat, right? This is horrible, okay? So we started asking ourselves, well, could you imagine for the low-value energy application in your electric vehicle, heating the cabin, could you have a low-value battery, namely a thermal battery? And for the high value, basically retain your expensive, high-energy battery for the things you need it most, which is actually to move the car. And so we started thinking about that concept, and what we quickly realized was that even in some basic materials, if you look at metals and in storing heat just in the phase change and sensible heat of the metal, or so that's on the hot side. On the cold side, if you just think of ice, how much energy can I store in ice? And you calculate the energy density of something like ice relative to something like a battery, it turns out it's not that bad, right? Just ice has about the energy density of a lead-acid battery, right? Which at a system level is basically where your lithium-ion battery in some of your commercial vehicles are today, once you add all that system stuff. And so by making advances in thermal storage, we could potentially end up getting back that 35% range or downsizing the big expensive electric battery by having a very cheap option for the thermal side. Sort of totally wacky idea. So hopefully, this gave you a little bit of a glimpse into the future of electric vehicles and electric vehicle batteries. A lot of different angles there, right, which is part of what we do. Just to close, I wanted to go back and look at the past again. And I think it would be anathema for me to be here at PARC giving a talk as an ARPA-E employee or any ARPA employee without invoking some of the history of this place. And specifically, I'll point to this guy. I think the folks at PARC probably know who this is. Others may not. But this is a guy named Bob Taylor who, as a young guy, not a PhD, not an expert in computers, got hired into that original ARPA agency and got put in charge of a project on computing, which ultimately was called the ARPANET. And this guy and his boss basically had a vision of what the future could look like. And this, I think, for anyone who's doing the job that I'm doing, is the dream story, right? Which is, here's someone who had a vision of what they could do. They didn't have all the ideas, but they basically said, we can find folks who have the ideas. We can support a community. We can come up with a vision and some funding and try and seed something big. And when I read back at what the early ARPA folks did, these lessons that I talked about that we're starting to learn and that we use as a philosophy at ARPA-E, they're not new, right? This is all out of the original playbook, which was, question assumptions, which, right, was take a fresh look at things. It takes a village to have these things happen. And so, I don't know for sure, but I'm going to just imagine that this is the Bob Taylor picture when he was at ARPA, very officious, offices here. Maybe not, because maybe in DC he'd been wearing a suit or something, but I don't think so back then. When he left ARPA, Bob Taylor came to PARC. So he might be more familiar in this picture, right, the hippie beanbag picture. And I guess I'll just close by saying that in this case, right, we had the ARPA vision first carried out at ARPA and supporting a community. And then Bob Taylor came to PARC, and he built a team of folks here who kept working on that vision. And what's amazing to me is if you follow through the ideas back from ARPA and the people that were funded at ARPA and then working on this at PARC, right, you can basically get to every single idea and company that changed the world in the internet. Okay, and so my only hope is that one of the programs we're doing at ARPA-E ends up having this impact, and that we not only sort of change what might be possible, but actually change what this country and the world look like. So that's my encouraging final words, and thank you again for the invitation to be here. I think we have time for questions, yeah? Absolutely, yeah. PARC questions are going to be redirected to the PARC folks. Anything historical, I just pretended to know the history.
Did you guys at ARPA-E work with Boeing on the battery for the Dreamliner? No. We, yeah.
We're not, although you know, I think it's a fair example of some of the importance of some of the work that we're doing. I don't know more than is publicly available, and I think you know there have been some reports out on what happened. You know, I think ultimately these things are, you know, these are really complex systems, and so you know I think our view is that lithium-ion as a chemistry, it's been around long enough that certainly lithium-ion can be made safe, and you know. Is a really powerful tool in our arsenal of new technologies for energy. And so we're still supporting a lot in that space.
Thanks for the great talk. Apart from cost and energy density in batteries and safety, self-discharge can be a problem. And when you talk about thermal storage, that can be probably even a bigger problem, because if you want to store heat, not sure if you have insulators good enough to let you stay overnight and then have your car heat up in the morning also. Can you talk a little bit about that?
Yeah, no, I'd love to. So that was one of the things that was interesting to us, which is, okay, so you're excited about thermal storage, what do you try and support? And on one hand, you say, well, we'd like to get the energy density better, and so this might be new materials that can actually store more thermal energy. But then you have this issue of, okay, how do you keep that thermal energy in there? And so we do see opportunities around better insulation. Probably for us, and what we ended up funding in the HEATS program, you can look it up. For us, actually, the more interesting approach was to say, you know, when we do chemical reactions, any reversible chemical reaction is basically a thermal storage mechanism, right? We take two reactions, we bring them together. If it's exothermic, we get heat, or rather, right, if we can pull them apart, right, we can suck up heat. If we bring them together, we can get heat back. And when the reactants are apart, you have no leakage, right? And so a number of the efforts that we're funding on the thermal storage side are basically more chemical reaction-based methods for thermal storage. And if you think of adsorption-desorption reactions, there are actually ways where you can get both hot and cold storage in a single system if you design the system elegantly. Any other questions?
A lot of this breaks down into the ideas of you don't have a lot of energy, we need to carry more energy to get where we need to go. Another portion is what if we could go as far with less energy, basically carry more or need less. What about, you know, the reason we carry a battery anyway is because the energy is not with us. It's farther and farther away as you drive farther from home. You know, part of it is there better access to energy through roads or charging up at stoplights or something? Is there investigations of like that sort?
Yeah, so I'm trying to think if there's anything I can point to that we've funded at ARPA-E. I mean, certainly the flip side of the electric vehicle, kind of one of the scenarios you should think about is there a way to dramatically increase the availability of charging infrastructure and make that more ubiquitous. There are a lot of ideas out there. We are funding some work around kind of bringing high power through fiber optics. Actually, this relates to some of the fiber optic stuff that I talked to. And you could imagine maybe delivering power to many more spots on the road through fiber optics is, you know, just sort of a kind of zany idea. But it's something that we think is really important as one of those scenarios. We don't have any programs specifically focused on charging infrastructure. The Department of Energy as a whole now has created an initiative basically thinking about how do we bring about electrification of vehicles more quickly, called EV Everywhere. And that's meant to be sort of an all-of-the-above approach where they will be funding likely, I can't say for sure, but likely part of that is meant to be infrastructure as well. So I think you're absolutely right with the question.
Seems to me that the biggest barrier to widespread adoption of electric cars is the time it takes to charge up as compared to the gas model. And so I didn't hear you talk about solutions to that, whether it's, you know, replacing a battery or pouring in electrolyte or those kinds of things.
Yeah, I think it's a similar answer, which is we agree that charge time is one of the barriers. We've sort of bounced around the idea of could we do a program that relates to a super fast charge battery. But then you basically say, most likely if it's a very high power system, it's not going to hold quite as much energy, and so you'll need to worry about this infrastructure, ubiquitous infrastructure problem, and you know, we haven't quite figured out how we want to struggle with both of those. We are seeing opportunities for batteries that can deliver and charge at much, much higher powers than today's batteries. And we just funded a number of projects in a wide open solicitation that we did. I guess I'll mention one small company called Alveo, which is based on work actually out of Stanford down the road, looking at a new chemistry which could be dramatically cheaper than today's battery chemistries, and still allow for very high power. In that case, they're looking at that storage for the utility grid as an initial market, but we see opportunities for that to maybe spill over into automotive as well. You know, one of the things that I didn't mention here is a thing that we struggle with at ARPA-E generally is actually doesn't really have as much to do with technology, right? But the question of what are the big barriers to adoption of electric vehicles, and what is the right scenario, right? Is it, right, would everyone in this room rather have a very small lightweight battery that could get them 300 miles but they have to wait 5 hours to charge it at home? Or would you rather, you know, pay more for the charging but have more chargers and then, right? We actually don't know which of those is the optimal scenario because it depends a lot about a dramatic shift in consumer behavior, right, that we can't predict. And so that makes it hard for us sometimes to figure out, well, which of these futures should we really be supporting? And, you know, again, it forces us to say, well, let's create the technology options and we'll see what happens. Yeah.
Could you share your personal opinion on why there are few volume lithium-ion battery manufacturers in the U.S.?
My personal opinion on why there are few battery manufacturers in the U.S. Well, there are more than there used to be. I think, yeah, I think there's a simple answer, right? Which is when we were searching for the next big battery chemistry after nickel cadmium, right? The whole world was searching for it, and a lot of the pivotal research for lithium-ion happened here in the U.S. It turns out that the first big thrust commercially came out of Sony in Japan. And by the time the US companies tried to switch from the existing technology to the new technology, lithium-ion, it was almost too late. And they couldn't be competitive in the global market at the time. And so we had a case where the entire market really, from a manufacturing standpoint, developed over in Japan. What we're really hoping in DOE is that we don't let that happen again, right? And that's why we're really thinking about, you know, really needing to support these new chemistries so that ideally we do that fundamental research here and we also capture the opportunity here.
So it's 6 o'clock, so why don't we stop here, but we still have 30 minutes for people to talk to one another. We have some refreshments out in the lobby, and let's thank Ilan once more.
Thank you. Thanks. It was fun.